turn off. But it's
Oh, you can hear like.
yeah.
Yeah, we turn off.
And they have like cappuccinos, and they have like candy.
But like it's also fun. It's also fun.
What are they doing here?
It's also right.
Doing now again, by the
Hi everybody. What happened to the attendance? Where is everybody?
Some people say 2 or 3.
Skiing.
That should be, yeah.
That should be the right board, actually. Yeah. Then, yeah, I have no solution to that. That is why, actually, I have on my. I'm actually a fan of slides with few words. But since it's also your course material, there are obviously a lot of words in my slides. But for today, I put in orange things that are I want to stress. What I will have put on slides if it's just a presentation. And finally, I also have now a clicker, which I lost my on before. So good. So today is about finally my area where I do most of my research. So climate change, integrated assessment models, the social cost of carbon, what is optimal emission reductions, how would we optimally transition to low carbon, to net zero emissions. So we're going to see the simplest climate model that is well published, that is my model, and then we also have, there is a nice paper of a series of people who took dice and then updated it with many different discount rate, but then also a different damage function, better climate physics, etc. And then see that with DICE. DICE is the integrated assessment model of the of Nordhaus, the Nobel Prize winner in integrated assessment modeling. And so normally DICE gets you to 3 degrees or shows that it's optimal to be at 3 degrees or 3.5, but then if you use these other parameters, they show that it's also optimal with other parameters, it's optimal to go below 2 degrees. Simon Dietz has written a very nice overview on integrated assessment models, so that's also very good. So that's the main reading list, and then there are 5 or 6 articles related to things that I will show as the additional. Let's start with so the social cost of carbon is the sum of all future damages, present value of future damages of 1 ton of carbon. Is the carbon price, optimal carbon price. Who would situate it below 100 pounds? So let's say everybody has to vote. No. So this is just to see a bit where we what before the course is your opinion. So below 100 pounds per ton for optimal price. Okay, we have some people, and then who thinks it's above 100? Yeah, slightly more, let's say 1/3. Good. So, yeah, we'll see what you think after the course. One element is that it will depend on your discount rate and therefore also on ethics. So there is no right and wrong answer. Yeah? And maybe as a spoiler, I think 100 is quite a reasonable value. 150 can be reasonable. Good. So, first point, for an integrated assessment model, it's integrated in the sense that it has science and it has economics. So what's the science? So here is, I've actually myself written a paper, do economists get the climate right, and does it matter? Short answer was actually they didn't get it right. So we had a look at 7 of the most famous economic models, and so this is what comes out of the science models. So it's this is time, and it's the impact in temperature for a pulse of emission. A large pulse, but that actually doesn't matter. So it gives you rapid increase. If I emit today, I see within 10 years a rapid effect on temperature, peaks at year 10, and then it's constant over time for more or less 100,000 years. Okay? Now, what did most of the models have? Basically, DICE had this. So DICE in 16 used this impact response function. In 13 had this. In 2013, this response function. All these economic models assume that there is 50 to 100 year delay between emissions and peak effect. That's bad. And I think they all changed after this paper. So now it's important to understand that if you emit a ton of carbon, your warming comes fast. And then you have more or less eternal effect at this red level. And there is quite a bit of uncertainty on how large this effect is, but there is no uncertainty on the fact that it's going to warm fast. Yeah. And a nice approximation is to assume that when you emit at time 0, you get this and then a constant effect. And if you do that reasonable approximation, then you get a system where actually for each ton you get an immediate effect that is constant, and that will give you a level of warming that doesn't depend on when you emit. The only thing that matters is how much is your cumulative warming. And so here we have how much is your cumulative emission? Here we have cumulative emissions since 1950. We have warming. And so these different colors are different scenarios going from very rapid reduction of emissions to an increase in emissions. So SSP5, like this one is the hottest scenario. And it shows that whatever scenario you follow, the only thing that matters for temperature is how much cumulative emissions you have. All the lines are almost the same. And second inside, it's linear. It's almost linear. And so you can just assume here that the change in temperature is just proportional to emissions. Yeah, if the temperature is explained by the integral of emissions, the change in temperature is just proportional to emissions. That's what we're going to use. It's a very good approximation, much simpler than what was used in the economic literature in the past. Then, next element, what will determine the integrated assessment model is abatement cost and damages. The basic logic is you set marginal abatement cost equal to marginal damages, and that will set your optimum. So how does this look like? So this is emissions, and on the y-axis I have the cost per ton of emissions, and each block in this approach would be one technology. And so we have agriculture, so here we probably have something to do with rice management. Rice is very polluting. Creates methane because it has a wet phase. And then, more importantly, for power, this is probably solar power. Yeah, we can avoid 2 gigaton of emissions per year with solar power. And we see then here that the height of this column is how costly it is. So here they say for this, it's solar or wind, it's going to cost 50 euro per ton. Yeah, and then you start with these. Some things are cost effective. You win money, you gain money, and it avoids emissions. Maybe like LEDs. LEDs do not. You save more energy than the cost of your LED. So it's cost effective, and so then it has a negative cost, and you also avoid emissions. And so as you have done most of the cheap stuff, more expensive things remain. And we go, like transport tends to be more expensive, whereas there is in agriculture and forestry. So here maybe we have some reforestation that is quite cheap. These things are relatively cheap. And so you order all these technologies according to cost, and you have a marginal abatement cost function. Yeah. This, yeah, some explanation of what is in there. And this is then how this evolves over time. So this was the estimate 7 years ago, and then as time evolves and technology devolves, these costs go down over time. You'll see that at the end, how you take that into account. And then this tells you that although this comes from the same study, it's Goldman Sachs, that in practice, when governments apply programs, often subsidies, for green technology, they pay relatively crazy prices. So that is one reason why a tax works much better than a subsidy. You have to over-subsidize to motivate people to invest. That's often, and you give subsidy to some people who would invest anyway, so it's a lot of, it's good for richer governments, but it's quite expensive, requires quite a lot of funds for modest emission reduction. So here we are, electric vehicle battery subsidy between 400 and 600 euro per ton. Or cash for clunkers, that is paying to take old cars off the road, between 300 and 400, wind energy between 0 and 250, etc. And again, solar between 100 and 2000, depending on which subsidy scheme. Good. Similar, this is biomethanol. So it's an expensive technology. So you can make, methanol is something quite close to gasoline. So once you have that, you can go in airplanes, you can go in boats, you can do many things. But it's quite expensive, especially if you make it from electricity. So then you take CO2 from burning biomass, you add hydrogen from electricity, and so then you're between 1,000 and 380 per ton CO2. Yeah.
So the came before that
Governments tend to overpay when they're subsidizing green. So,
Why is that?
yeah, why or who's writing on that?
So this was a study, Gillingham in Yale. So what I know from Belgium is, and I think that is generally the case in Europe, governments are very slow. And so they start with subsidy, and then they have a given budget. But then as the technology evolves, it becomes more cheaper and cheaper. So solar panels are now 10 times cheaper than 12 years ago. And so the subsidy is too high. And so then it took me half an hour, because I'm in president of the climate change committee in Wallonia, south of Belgium. It took me a long time to explain to the government that if you run out of your subsidy budget, you have set the subsidy too high. So they're just like, they're very much into like a quantity logic. Okay, we want this amount of solar panels, we put a subsidy, lots of enthusiasm, the budget is spent, mission accomplished. So they have no clue that actually with the same budget they could have done more. Like it's just like, they think the box is fine. So that is lack of economic understanding in governments, but obviously in governments you also have people who understand that. So it's more like you have an electoral cycle. They put the subsidy at the start. They're not going to change it within the 4 years that are coming, and then the next government reduces it. But then it's reluctant to reduce it because you lose votes. So once you, so that's this mechanism of trying to get votes with presence. Good. Next element, a damage function. How much damage do we get for whatever warming? Well, let's think of 3 degrees of warming. What would be, how much percent of GDP do we lose? Maybe we can do a vote. So we think we lose 2%, less than 2%. 3 degrees of warming, less than 2%. Who thinks less than 3, between 2 and 3? You have to vote, no? Because if not, you're cheating. So the question is, we have 3 degrees of warming. What is your expected loss in GDP?
Are there 2 options or 5?
No, there are many. So between 4 and 3.
4 and 3?
Yeah, 3 and 4, yeah. Then, okay, we between 4 and 5. Yes, between 5 and 6. Above 6? Good. Okay, so actually we have a very modest understanding of how much damage we're going to get. So this is just from last year, a literature review, and both are stern climate concerned researchers. Yeah. So we have, let's start with Nordhaus at the time. So Nordhaus, much long after he got the Nobel Prize, but so where we were like 10 years ago, actually it's 9 years ago. So he has 2.5% GDP loss for 3 degrees of warming. Then they have the more recent studies have found larger damages. So now Nordhaus 2 years ago is at 3% loss. Then this paper does like quality weights on studies and corrects for the fact that some authors have many studies, so that should also have a bit different weight. So when you do a literature regression, there is a lot of art in putting weights, and they use that from the medical science. So they have typically this problem of 20 studies measuring the same thing and this very different outcomes. And so then you also need to look, they look at sample size, they look at double-blind electric quality indicators, and so on. Anyway, so let's see the largest, if you have growth effect. So that is maybe something I have to explain. In these regressions, you can impose that it is the logic from this graph is a level effect. So if you think of the world with 3 degrees, you think of GDP being constantly 10% lower or whatever. But that means once you have taken the hit, you again grow at 2%. Now you can also say, if there is 3 degrees, we can't grow at 2%, we're going to grow at 1.5. So now your damage is growing exponentially over time, 0.5%. And so you get explosive damages. I think we don't have good cross-sectional evidence that warmer countries grow less forever. So that would mean that Norway is below optimum. You know, like it should be very poor. You would get ever increasing differences between countries with the best climate and countries with less good climate. Like Miami would have like ever increasing, should be much poorer, like infinitely poorer if this goes on for a long time. And so that, maybe it's true, but then yeah, I'm a bit reluctant to think that there are large growth effects.
Are there sort of things in the middle where you sort of have a reduction in growth, but then this reduction in growth decays over time? So that we then get to the same growth level over a long term again?
That is actually level. Because obviously when you lower the GDP in the transition, during the transition you have lower growth. If not, you cannot go to lower GDP. But then a pure level effect would mean in the long run you get to like the same rate. Which is also maybe it's a bit of, yeah.
How do these models deal with climate shocks, repeated climate shocks? So you said there's like one shock and then the growth rate the GDP drops and then grows as before. But what we expect is at like 2.5 or 3 degrees, right, that we have like this flood and that, you know, like constant shocks. And so how do they do that?
So what they now do is they just run a regression and they look at hot years and how the growth is lower between hot years and warm years. And a growth effect means you have missed some innovation opportunity. You have a hot summer. Now you have an eternal effect forever. You will never catch it. That is a growth effect. The level effect says you take a hit, bad harvest, and then the next year, if it's normal weather, you're back. And so then they think of warming as a repeated shock. So it's very hard to include adaptation. With adaptation, you overestimate. It's very hard to include the logic of repeated shocks. Technically, you can do, like you can say, I have a dummy for a repeated shock and see if that is larger.
But just basing it
So I think that I have to think a bit harder. If you say, whenever I have a repeated shock, it's worse, then I think you get into a growth dynamic. Because warmer world is a repeated shock every year, and you never adapt to that. And so even this, like the same 2 degrees gives you increasing and increasing damage because of the repetition, and you will get mathematically the growth effect. The growth effect can be justified by repeated logic.
Well, on this point of the shocks, actually, is it clear the relationship? Because I think that, so bad harvest clearly is negative for GDP, but fire, for example, is very different. It boosts the GDP because there's a lot of reconstruction and so on. So there's a distinction between welfare and GDP. I don't know if that comes into play because
So definitely true. So certain disasters can give a boost in GDP because they generate extra construction, like reconstruction as an activity. GDP is not a welfare measure. But I think it's among all the difficulties in these studies, it's a minor one. So normally, if there is a fire, you would get a hit. Some people can't go to work. Some I don't know how GDP exactly measures the destroyed value of houses. That might not be in GDP. So then that would, but this, yeah, it's one of the many problems. So my best take is we don't know. Because, so here now we have like this study. Yeah, I'm going too long, but let me just say two things. No, first maybe your question.
Yeah, just similar sort of question. I just wanted to make sure I'm understanding. So like, if these are looking at changes in like a specific period of time that was hotter, like if we're looking at extreme weather events, that wouldn't necessarily be included if they're looking at just like past years that were hotter that don't have those like extreme weather events that might be.
So studies look at hotter weather years, and then they see how that affects GDP, and they say this year is 0.2 degrees warmer, we have less GDP, and so that is in the regression.
Yeah.
And then they look at extreme precipitation, there is effect, and then they look at heat waves, so like the hottest day, and they look at cold waves and things like that.
But yeah, I guess I'm thinking of things like fires.
That would be implicitly included in a hot year. So let me then also say there is not only the regressions, there are also these studies that go start from disaggregated effects. And so they look at what is the effect on fire. And we're going to think of degrees warming, how much more fire do we get, what's the loss of it? Especially also lives. So how many people die in a heat wave? How do we value the lives? And then that would be a large component of the social cost of the damage. And then many other things. Floods, what do floods cost, etc. They tend to reach smaller percentages than this. So the key thing is, for example, here, Bilal and Kanzik, they now find damages that are 10 times larger, like they're much larger than even this line. But I had a student last year, a master dissertation. She adds 2 legs to the model, and the result is gone. Actually, with 2 legs, the model had the identifying assumption of the model is better. It's very hard to. So let me just say this: like, if you do regressions, you look at years that are 0.2 degrees warmer. Now you say 2 degrees, that's 10 times this effect. So you extrapolate 10 times, it's better. I'm not saying people should do it. I'm just saying we shouldn't believe too much this 10 times extrapolation outside the, it can be much worse and it can be much less bad because we have adaptation, etc. So I use a large value. Because that is how your model goes to 2 degrees, and I think today we want models that stay below 2 degrees because that's actually also Paris, and that's what we're talking about. It doesn't make sense to make a model that says it's optimal to go to 3 because the whole world has agreed to go to 2. So then, from reverse reasoning, if you believe in it, that 2 is optimal, you actually believe in a very low discount rate and or one of these larger curves. I think we use the old one, the purple one. Good. So the key thing is you need a damage function to make an integrated assessment. And the second key thing is very hard. to establish, and you can do reverse engineering, say let me put a given damage that is not too long so that I get a politically meaningful model that stays relatively. Yeah.
As far as I remember, I don't know if this was the first models of IAMs, but they measure the impact on economic output through temperature increases, and then how that affects productivity. But is there any other channel that they use, or all of this is just driven from increasing temperature and how that affects output, and therefore how GDP decreases? Like, is there any other climate mechanism that affects?
So actually, I've been, the reason why I was late first week, so in Gothenburg, I was with a team that puts climate or environment in the utility function directly. So it's this from last week, this discounting with two arguments, and so it assumes that some of things like coral reefs, we appreciate it in a different way from our consumption. It's not all consumption based. The problem is, how do you evaluate what kind of functional form? How do you verify like how much of our welfare comes from non-consumption? But it's obviously not zero. So that's an interesting strand of work. Actually, biodiversity and climate, I want to do it, but it hasn't been done. It's hard. Yeah. So then, yeah, two questions.
Are the papers that take a different approach, sort of in the sense, because to my understanding, this is mostly looking at like, okay, what from past data can we learn about like what GDP growth will be? Instead, papers that sort of like look at it the other way around, like, okay, let's say we have a 10% reduction in GDP. What are the different sort of things that would actually mean in the real world? And then you could sort of do more plausibility check, like this 10% reduction would come from X losses in agriculture and X losses in like industry, and then you sort of have it like a more.
Yeah. So that exists. So, but they would say, let's go like bottom up. What are labor productivity losses in heat waves? What are deaths in heat waves? What is the cost? Like all these different things, and then they add it up and they arrive at certain damage. I like that actually. It's a different way of getting there, but then some economists would also say, yeah, but like the effect on innovation, how do we measure that? Like maybe it's bad. Now we get growth effects. The worst scenario. How do we see? No, there is a study. So they were looking at researchers when they move to a hot climate, do they get less patents? But like, how, like, I come to London, it's cold, I shouldn't be productive. But obviously by moving, other things are happening. I go to the other seat, sadly now that I'm productive, so it's gonna, there's only so much you can see in data. So sometimes we have this wonderful idea that you can see anything. But it's like this question, I would say, luckily we do it, but you can't get very far in the. You had,
Yeah, sorry to come back to this again. So the only studies that are included in like to estimate what the effect of global warming on the GDP is studies based on, okay, there were hotter days, or we compare hotter countries to colder countries and things like that, and not like, I was thinking of like in my master's I worked on physical risk and central banks, and they like estimate the, like with macro models what the effect is of, for example, like climate change reduced inflation, for example, that harvests, so like lower I don't know, higher prices because the rivers don't work as they should or whatever. And then the central bank has to raise the interest rate, and then growth is more again. Like, I mean, there's a whole strand of literature also looking at this. Is this not included, or is this?
It's included. I think these literature reviews include also these studies. Okay. Yes, but I think I've seen from macro literatures. No, it's more like the effect of climate policy. Does it increase or decrease prices? I think mostly said increases, but it's even that relatively simple question is hard to answer. And you will need modeling. You cannot just look at temperature and pressure. You can do that actually, but then these tiny effects, you get measurement difficulties. Okay, so let's for now assume we know the damage function, we know the marginal abatement cost function, which by the way is even more, it's similarly uncertain as the damages, and we have an agreement on the discount. So all, and we also for the climate physics have an agreement on what is exactly the climate sensitivity. Yeah? The four are very uncertain. Good. So then we go to the simplest climate model. So we have, this is, I've explained this. Define cumulative emissions as just the sum of all past emissions. Then temperature, yeah, I've told you, is proportional to cumulative emissions. Now we get, here is our basic model. So we get so we have a discount rate, and we do two things. So there are benefits of emissions. That is the marginal productivity of a ton of emissions. It's, or the derivative of that is the marginal benefit of emissions. And so it's also the marginal cost of avoiding emissions. Yeah. So the derivative of this, so this is total benefits from emissions. And this is the damages from cumulative emissions. Because damages are driven by temperature, so it's the stock that determines the damages, and it's the flow that determines the benefits. And so we have a Hamiltonian, very simple. So the first order condition tells you that the shadow price is the marginal abatement cost. What is if I start today with 1 ton of emissions emitted less in the past, my cumulative emissions is reduced by 1 ton, I'm going to get, my welfare is increased by the marginal abatement cost. Yeah. Then, co-state equation, we get this, this simple equation, which I rewrite in a way that is more intuitive. So I have my optimal path, and I'm thinking, what is the effect of emitting 1 ton less today, and then I emit 1 ton more next year. So with this 1 ton less emitted, I'm going to put money on the bank account, yeah, and that will get my return R, the discount rate. Now, what is my cost? So this would be my return if I postpone, or it's what it costs me to bring emissions forward. So one thing is, next year, the marginal abatement cost is higher because I'm on an emission decreasing path, and so the cost to abate the next ton is always higher than the preceding ton. As I abate, my costs get more and more expensive. Remember this abatement cost function? And so I'm abating more and more, and the cost increases. So that's this one. And then here is another one. If I postpone by 1 year, today I get the marginal damage from that extra heating. So there is 1 ton, in 2 years it's the same. So the temperature is back to the normal path. But if I postpone 1 ton and I abate it next year rather than today, today is hotter. And so that is your marginal damage divided by the marginal abatement cost to make it a return. Yes, let's start with the lady.
I have a question about the slides. I assume that the lambda is supposed to be a mu, and it's 1 2.
Where's the lambda?
And substitute out lambda in 2 and 3.
Yeah, okay, yeah, exactly. Very well split.
It's just
mu. Most of this literature uses lambda, but then at some point we'll see later, I'm going to use lambda for the present value and mu for the current value shadow price.
necessarily that the second term, this MAC over like derivative of MAC over MAC, that is positive because like if I think about, for instance, Nordhaus, I believe he has sort of like a 2% decay per year of like this marginal abatement cost curve dropping, like because of technological innovation. And if we sort of go less in this direction, it goes down and could actually be negative, right?
There is one paper on declining carbon prices. I like the author. I think he's wrong. It's well published. And it's with a method from finance that I don't master. So let's say maybe it's possible, but I think it's not. But I have the formula. I published a paper last year where I might have proven that this is impossible, but I'm not sure. There are many proofs in that one, but I've written them. They are my proof. So probably not. Good. So we're close to the hoteling rule. So the price of abatement, the marginal productivity of our emissions or of our oil goes up at the discount rate. But then there is a correction. Abating earlier also gives you a climate dividend. You warm later, and so in the meantime, you have your damages later. Yeah? So the carbon price goes at less than the discount rate. That is what this cost-state equation tells you. Good. Steady state. So I just set derivatives to 0, and I get this simple equation. The marginal abatement cost at 0 emissions will be equal to the sorry, I go back. So in the steady state, the marginal abatement cost by the definition of the steady state is 0, the change is 0. So this one goes away, and I've only this left. Yeah, I'm gonna bring marginal abatement cost here, and so you get the yearly damage from 1 ton, yearly marginal damage, but that is avoided forever. In a steady state, if you have 1 ton less, you get an eternal gain from a marginal damage. And so the formula for an eternal gain is this. Marginal damage divided by the discount rate, that's the value of an eternal cash flow. Yeah? So that is your steady state equation that sets the steady state temperature. Marginal damage for the temperature at which the marginal damage divided by R is the marginal abatement cost at 0 emission. That is how I fix the steady state temperature. Good. Then other insight from this simple model, we had this, yeah? This was our co-state equation that we started from. Now, you can't solve that with separation of variables, sadly. So now we're going to use a good guess. That's actually the method that brings you the farthest. So what would be a good guess? Maybe you remember that if you use a present value shadow price, this term disappears. But maybe you don't. So then I'll show you, if you do take this as a good guess, you can see that the time derivative of this is a simple formula. And so now you have redefined your differential equation in a way that it is that you can separate the variables. So this is lambda, and then this is just a function of time, or you can think of it as a function of time. So I integrate this, and I get this. very intuitive relationship. The marginal abatement cost today, it's the marginal cost of avoiding 1 ton of emission, should be equal to the discounted sum of all future avoided damages from that ton. And that's going to be the marginal damage on your trajectory over the whole future path. Yeah? So this is the optimality condition on the path. This integral is also called the social cost of carbon. It's the present value of all avoided future marginal damages from 1 ton. It's the cost of an emission. It's also the benefit from avoiding emission. Okay? Then, that's it. So this is yeah.
I'm quite doubtful on the assumption of the steady state emissions, because you cannot discount the everlasting, like without emissions, right? Temperature will still rise because of like ocean thermal inertia and all this cumulative emissions, right? So then this model actually, it's not like time going to infinity, then no emissions. Then
yeah. So maybe when we stop emissions, there is no more warming. In my simple world, I have the warming is just proportional to cumulative emissions, and so if the emissions are 0, the warming doesn't change anymore. Now, in reality, if you go to 0 emissions tomorrow, you will still have the delayed effect of the last 5 years of emissions. So you would still go up 0.1, maybe 0.2 degrees. But in my simple model, it stops immediately by this simplification.
so they back in additional 5 years in like a proper standard climate model.
Yes, in good models you would have that, yeah.
Steady state.
Before going to a steady state, and then it can go a bit down. Comes out of this impact response function that I showed on the slide. So there's no more extra warming, and so then you will have quite rapidly a steady state. Except for the last 5 years of emissions, which had more emissions than ever, no? Like that's why it's non-negligible as 0.1. Yeah.
So in empirics, when we actually try to estimate that, would you rather estimate marginal damages or the abatement cost? I mean, in optimality, they should be equal. So to estimate the social cost of carbon, which one would you take if there's uncertainty? Potentially both.
So this is what we are measuring with econometrics, the damages from hot years. So actually, it's since S is just proportional to temperature, you should think of this as the marginal damage from a degree extra or from a centidegree extra, yeah? And so this is what we are estimating. We don't have optimal policies, so we cannot from this equation infer, or you would say we assume that politicians actually think we're on an optimal path, and then you can see from here what they believe about the damages. But that I don't think people do that. I don't think people believe we're optimal. And on future abatement costs, we have engineering studies with no observation. Yeah. So what is the cost of hydrogen if we go full in on hydrogen? We have to guess. We got it like systematically wrong for 20 years on photovoltaics. It's going to happen again. But maybe now we're overestimating it. Now it's more expensive. It's just hard to predict. Good. That is an argument to get at least the mathematics right. No? At least there is no discussion there. Good. So now we're going to make it slightly more realistic and also to get a closed form solution on how the emission path evolves. and how you go to a steady state. I'm going to be relatively fast. So this is just a paper, you can read it, and even like you can just follow the equations. It's relatively straightforward, and I also do this in the seminar. Not the general solution, but the cost effectiveness one. So here is what we. I'm sorry that the orange is actually not that visible on a screen compared to on a big screen rather than on a computer. Anyway, here it is. So consumption is a constant. That is consumption at time zero with zero emissions, and in the hypothesis that there would be no damages. Then this goes up at 2% per year. Then we have this function. I'll come back to this. This is the abatement cost factor. The more we abate, the less we consume. Or differently, the more we emit, the more we consume. And this is just quadratic temperature, so this gives you this convex damage function. Yeah, I'll come back to this. So we have the derivative of consumption with respect to temperature, but I have written it in cumulative emissions because that's going to be easier later. So temperature is just zeta times S, and so this is our expression for marginal damages. Then marginal abatement cost, it's a marginal productivity of an emission. You get linear abatement costs, proportional to your production or your consumption. And that's it. So this is from our paper. It's the old IPCC report, and so we show that maybe you believe that abatement costs are linear. We have a more recent paper testing this econometrically, and we find actually that linear is a better fit than quadratic marginal abatement cost functions. But they're a bit different in the sense that for the marginal abatement cost at zero emissions, I've taken the cost that we would reach once we're there. So that's the cost in 2050 or 2060. Yeah? And so that will have included some of the learning. Good. So standard stuff, standard welfare function. We add growth of population. So L for labor, yeah, grows at rate N. And so welfare function of always. One thing is, it's quite common to say that if we have more people alive, this period is more important. If twice people alive, this, like every person has the same weight. So that means welfare is proportional to how many people are alive in a period. So the Hamiltonian, nothing special. That is just basic equation against that saying the marginal abatement cost in utils is the shadow price. Same logic for the dynamics. And the next step is we have the co-state equation giving us lambda dot. We have first order condition giving us lambda. If we take the time derivative of this, then we can substitute out lambda dot, and we get our Euler equation. We've done this in week 1, week 2, week 3. So that is what it gives. So again, two equations, you calculate the lambda dot in two ways, and you have your solution. So the solution is this. This is just the Euler equation with one annoying thing. We have the consumption growth. Yeah?
A question on that consumption. If we assume that economic growth is larger than population growth,
yeah,
then total consumption would not be C equals to C times L, no? Wouldn't it then be larger? If we assume that with economic growth outpacing population growth, then what each person consumes actually grows.
Yes. I'm not sure if we So we assume that total consumption is, so the small c is consumption per capita. But total consumption grows at 2%. I think that, sorry, this was small. Yeah, this is consumption per a unit per person. So that grows at 2% TFP, but then we get 0.5% population growth on top of that for 2.5% of total GDP growth. That is what it says. And like we can have fast population growth or lower, that's quite free. But the model cannot be solved if your population growth is larger than the discount rate. Maybe I should. That's a technicality. So if population growth goes faster than the discount rate, then you get an integral that is infinite. So this becomes a positive exponential, and you can't solve that. But or you would need different. There is a way to do that, but yeah, you get into technicalities. But we're going to assume 1% pure time preference rate and 0.5% population growth, and that would not be a problem. Okay. So then, so we're here. Euler equation, as always. This is our co-state equation where we have substituted out the lambda or the mu. And now a simplification trick. So consumption is not exactly 2% because we're going to have abatement costs, so we're going to grow less fast. And then we're going to also have damages. So that again makes us grow less fast. Even though we have level damages in the transition, we get a less fast transition. Now, if you look at these costs, nor the damages nor the abatement costs can affect the growth rate by large. So we're going to assume that we see that we simulate it, and it's never more than 0.2% of the growth. So we're going to assume a slightly lower constant growth rate to solve the model. Yeah, that is an interesting point that you can make to policymakers. Like for the transition, we're going to need a growth like quite a lot of costs, maybe 5% of GDP, but that is spread out over 50 years. And so it's 0.1% of growth that you lose to save the planet. No? So it's, you wouldn't notice it. It's not that we need to kill all growth or that there is no growth possible. It's, even if 10% of GDP abatement cost is large, or maybe 5% of GDP abatement cost, it would not stop the growth. For us, this is just a technicality. So what was an annoying time derivative is now a number, 0.98%. And then we get this solution. Again, it's the Euler equation where I've used this approximation. Yeah, it's slightly below 2%. And so I have a differential equation in my decision variable, emissions. I have a differential equation in my stock variable, and you can solve that. Now, this turns out to be, I can take the derivative of this, and I can rewrite it as a second time derivative. So I can put the two differential equations in one, or not. You can just solve this. It's linear, so it's a constant times E, a constant times S, minus a constant. And for linear differential equations, we have closed form solutions. Now, you can study a big book on closed form solutions. Or you can ask ChatGPT, or here, like this is from the time ChatGPT doesn't exist, Wolfram Alpha gives you solutions. So you just say, I'm looking for a second order differential equation. So this is my E dot dot. Then I have a constant times E dot plus B times E minus C. And it gives you the solution. So to be honest, I can't solve that, no, or it's hard. But then that's why we have computers. Okay, so we have this solution. It's K1 and then an exponent as a function of time. And then there is another, it has a different sign, and that's it. Yeah? So we have the solution. We just have two integrating constants because we had two differential equations. Same story as always. And so one is, this is actually, so this is emissions, remember. This is positive. If K2 is not 0, my climate is going to warm forever, ever faster. So I have a node that will blow up, will violate your transversality condition, so that's not possible. So as a result, I know K2 is 0. The other, if it's not 0, it doesn't make sense, nonsense. What would be the other integrating constant that I can use? It's an obvious one. But, yeah.
Emissions is pretty 0 times, like.
Yes. So we know the cumulative emissions today, or we know the temperature today. Yeah. So it's the initial condition. Like for the savings model, we know capital today, or for the oil model, we know the stock today. Yeah. Good. So you put that in, and there we are. So this is our solution. This is so this. We now have the stock as a function of time. That's it. Now, if we take the time derivative of this, we have the emissions as a function of time. And we can also look at the carbon price. So the marginal abatement cost gives you this formula. And we can set, we can say, what if time goes to infinity? Then we get our steady state. Or in preceding equations, we can put these time derivatives to 0, and we get this equation. So the optimal steady state temperature is just the product of 4 things that are very uncertain. So the first thing is it's proportional to your discount rate, but even worse, it's discount rate minus the growth rate. That's even more sensitive to the parameters of the discount rate. Minus the growth rate, that is because we have assumed that damages are proportional to GDP and abatement costs are proportional to GDP. Then the other parameter is the marginal abatement cost at 0. That sets the steady state. We've seen it already. So you have to estimate what is the most expensive thing we're going to do once we're at 0. There are a few candidates. Direct air capture, just sucking out CO2 out of the air, or BECCS, burning biomass and burying CO2 underground, or some very expensive hydrogen application. Any of weathering, mineral weathering, so you can crush minerals and then they will absorb CO2, also quite expensive. So 500 euro per ton, maybe 1,000, not more actually. And then we have the transient climate response rate. So the slope of this relationship between cumulative emissions and temperature. Think of it as the climate sensitivity. How much warming do we get for each ton? We don't know that very well. And then the damage parameter, how large are the damages? Very uncertain. but easy formula. This has been used in applications. So here is the solution. This is a simple model. Starts at a carbon price more or less of 50, and then this goes up. And at some point we're at negative emissions. Let's see here. No, that's the next. Okay, so this is a price path. You can get there with, starts slightly below 50, and then it goes up. There are better models than this. This is good for your understanding. We have more realistic models. Questions? I'm gonna do the, no, I'm gonna have a break because you're gonna be exhausted. So 5 minutes break, and then with the cost and benefits.
Stealing, yeah.
I was at the same time. I think for shoes. Session. Because you would get the same problem. The point is, markets, there is less scope for free riding because is counted future. Is punished for the damage that they give. The negotiation is prices move forward more than elections. And so it's an interesting one. It's still by the 33rd. The optimal world, where people would follow your opportunity by people. I was thinking, my question is, no question. Oh no, I did dirty only, and that might create arbitrage, like these people, these independent people. Easy. I'm not quite sure to have this world where you say, okay, I'm a global investor, I want to go to the share stocks. My other shares going up because now I have less damages. Then I have buys clean, buying dirty. It's a bit easier to solve. Yeah, because they might even oil value further. Let's start again. So we're continuing. Remember, this is the hard part. So full attention, please. Good. So we have done wealth maximization. We've done cost benefit. Now we do cost effectiveness, cost minimization. For a given target, imagine I want to go to 1.8 degrees. How do I go at lowest cost? Yeah. And so I'm going to just say I add this constraint. It's forbidden to go beyond 1.8 degree. And to make it a cost effectiveness, I'm going to say there are no damages. I imagine I abstract from damages and I replace that by a temperature constraint. Yeah? The entire IPCC is this. There are no damages in the IPCC, and it's a well-defined problem. So I keep the same structure, but it's not actually welfare maximizing because I'm ignoring damages. But I've replaced that by temperature. Yeah. So this is being added. I now have a problem that we haven't seen. So this is a problem with a constraint. You're going to need a Kuhn-Tucker term, don't worry. Technically, you're going to add this to your Hamiltonian, saying that whenever you hit the constraint, the shadow price becomes non-zero and it matters. The nice thing is, as long as you're below 1.8, the shadow price is 0 and you have your normal problem. So you have a normal problem. As long as you're not reaching the 1.8, it's just going to set a different terminal condition. This shadow price is going to set your terminal condition. Now, what could be a nice terminal condition, an intuitive terminal condition, once you reach 1.8? What should happen? Yeah?
Net zero.
Exactly. Yeah, 0 emissions. That is, you use, so you can prove that, it's a bit hard, but it's also intuitive. So you use 0 emissions at the end when you hit the constraint, when you reach the 1.8, and that is then well defined. So this is the Hamiltonian, again, marginal abatement cost in utils is the shadow price, co-state using damages 0, I get the hoteling rule. The marginal abatement cost goes up at the discount rate. And that now shows you that we're getting an error. It's not the same. And the scientists in the IPCC have not maybe seen that. So because why do they all do this? That's because in the time, the economists were saying we should go to 3 degrees, and the scientists thought that's a bit crazy, and they say, let's just minimize costs to go to a given temperature, because all this discounting, etc., we don't understand, like we don't know what the discount rate is anyway. Now, by doing this, pushing for this agenda, they didn't see that actually they get the incentives wrong. This solution, so you get, maybe for the similar temperature in the long run, you get a different path. So if this is this is time, this is the carbon price, marginal abatement cost. So this is hoteling. If for a similar long-term solution, warming, 1.8 degrees, I do cost benefit, my path needs to be less steep. Remember, I had an extra term, a damage term. And so less steep means, this is starting higher. I need to do more at the start. And so when you do cost effectiveness, what all the engineers and IPCC, etc. is doing, then you do less effort at the start. Yeah? So IPCC has 1,200 or 2,000 scenarios, but they're all cost effectiveness. Good. So we'll do this in the seminar, basically showing you that the marginal abatement cost, not in utils but in money, follows the consumption discount rate. Good. That's the seminar. So again, so our solution is now slightly easier. We get, for our paper, we get this as a differential equation. It is, again, but because of this constant, you cannot do separation of variables. And so you ask Wolfram alpha how to solve this, and you get this solution that we will use in the seminar. So this is then the result. If you say minimize abatement cost to keep your to stay below 2 degrees Celsius, you do this. So you emit more and then you go down fast. That is this green line, cost effectiveness. Low effort at the start and then go down fast, hoteling path. Now, if you say you maximize welfare to go to 2 degrees, you do more effort at the start and less effort at the end. That is, it also has become a paper in ecological economics from last year. Good. Now, yes.
Maybe that's intuitive, and I just don't get it, but why? What is the difference between the maximized welfare subject to 2 degrees Celsius constraint and then the maximized welfare where it's unconstrained but it's optimal to peak at 2 degrees?
So I think it's a bit irrelevant. So this is welfare subject. Yeah, sorry. Good question, because actually the contrast is the blue line versus the purple. If I just say maximize welfare and I've chosen my damage such that 2 degrees is optimal, it gives you this path, which does a lot early on and then emits for a long time, because these emissions are very expensive to avoid. And this is an intermediate path where I say, I think damages are low, but I'm still going to impose a 2 degree constraint. And it's an in-between solution that we're also advocating for. So even if you say, yeah, damages, we don't know, and all these crazy studies, like, I don't like it, let's just put a constraint. You can have small damages. Everybody agrees at least they're that large, and you add your constraint. And now you have an in-between solution. Yeah.
In the purple line, the temperature would actually go beyond 2 degrees, right? Because you never actually stop polluting.
No. It's a good question. So you would. I'm a bit puzzled. So the short answer is no. It's designed to have to go to 2 degrees. Now I'm a bit puzzled because the area under the two curves must be similar, and I'm not sure if they are. If they're not, I made an error in this publication. Very well published. Maybe it is. Maybe it's like but I think that this area is smaller than this, so I made an error. But you see the point, the general picture. You also see some highly published papers that have some problems.
Zero them, fundamentally.
If this is true, like it, yes. Unconstrained, optimal peak warmth 2 degrees. Yeah. I'll have a look. Or not, I mean, good. So how do you solve this with Excel? Maybe you don't like differential equations. Then you use Excel. So you can install a solver here in add-ins, in the options. And then you have something like this. So you see, you have here, because you've installed the solver, it's free, you get this extra button, and when you click it, then you get this window. So I have population, utility, consumption, consumption, utility. So you build your model. And so then you say, I have social welfare, the sum of all these utilities over time. And that is in this cell, and then you maximize it by choosing emissions each year. And that is, and since it's a cost effectiveness solution, you need to add constraints for an end of the world strategy. It's like an investing, like, the model would heat up the world at year 300 because you've stopped at year 300. It does an end of game strategy, and you can avoid that by saying, whenever you're at some point, emissions need to be zero in the very long run. Yeah. actually very simple, much simpler than differential equations. But with differential equations, you get insights that you couldn't get with Excel. So, good. Now, these models are very bad. No, like there are many things missing. So what would you add? Yes.
Any kind of political variable, so policies and policy effects.
Yeah, that's a very good one. So I've been wanting to criticize the IPCC because they have representative, I mean, I criticize them, but it's the point that they should include damage, dynamics of damage. But, and you'll see a further criticism. But so they generate representative pathways. But what is that like? I find it quite vague. So sometimes they, oh yeah, let's assume that it's not possible to have an early high carbon price, so we bring that in a bit later. Okay, so that's maybe realistic, but then that's an interesting scenario, but then you have to make the political constraint very explicit. And I think I don't have a slide for it, but I think, so these models all have one carbon price for the whole world. I don't think that's not gonna work. So you need an acknowledgement that poorer countries are going to do effort, but at a lower carbon price than rich countries. And so that would bring the carbon price much higher for rich countries and lower for poor countries. And that will increase the cost of climate, of zero emissions by a lot, say double. But I don't see how we would have one single carbon price in the world. So I don't have a slide for it, but it's an obvious one.
Just reinforcing feedbacks in the climate system. Like we said, 1 ton of CO2 does X degrees of warming, but it could be that like 1 ton of CO2 gets us closer towards like permafrost and like methane, and therefore it's actually maybe 2 tons of CO2.
Tipping points. I love it. I have a paper on that. Yeah.
Some uncertainty in risk aversion?
Yes. So there is a puzzle that when I look at risk papers, I do the risk model myself, but the mean preserving risk premium is very modest. And I don't believe it so much. So I see that, and also in my model, it's quite modest. Maybe I told the slide last week. So it's actually, I think it's a story about correlation between risk. And we saw the slides on discount rate, it's interesting correlation between shocks. Then your effect on discount rate is large. Actually, maybe connects to your idea that repeated damages might be worse than one-off heat waves. So I'll just talk about the tipping points, but then, yeah, you know that the mean preserving risk premium is actually modest in most paper, like 5 or 10% higher social cost of carbon. It does push the social cost of carbon up. That's actually also interesting. So climate skeptics would sometimes say, we don't know what's the damage. Maybe there is no damage. That's true. Maybe there is no damage, and maybe we're getting there. Marginal abatement costs go to 0 just by waiting. Maybe true, but if you put that in a proper welfare maximizing model, this uncertainty pushes the carbon price up rather than down. Mean preserving uncertainty is a reason for early action. You want to risk an insurance premium. No? And their insurance is early action, and so then when apparently climate change is not a problem, you can still burn the oil and enjoy.
Yeah, so physical and financial feasibility, because we are assuming assumption that needs to go up, we should go down, but change the technologies and can take time.
Yeah, so it's about, so I'll have slides on technical change. and how the analysis changes with technical change. I'm gonna start with the tipping points. Yeah. So there are many tipping points. So we have permafrost is a big one. So there is in the permafrost is the soil that is never that is permanently frosted, yeah, frozen. And so as we warm the earth, this thaws, and the methane that is in these soils comes out. Now, methane is a very potent greenhouse gas, and so you get extra warming. Then there are, so the West Antarctic ice sheet is a system in danger of collapse. But on average, the South Pole warms very little, and the North Pole warms a lot. So twice as much as average. On the South Pole, warming is almost not observed. So we're at 1.5, 1.3.5 degrees warming now. And so the North Pole warms 4 degrees. And land warms also like 2 and 1.7, and sea warms less. Yeah.
Why is that?
So it has to do with winds. It's wind. So the position of the continents and how that interacts with Coriolis forces and then these winds that go in you saw they turn, no? So very hard to understand. I don't know why. And here is an overview of also like at what level of warming they might start. And then Simon did a study on, it started as a literature review on what's the effect of each tipping point and how does that in an integrated assessment model increase the social cost of carbon. And they look at the tipping points for which there are studies that are published, to find the damage from that tipping point and the more detailed effects of that tipping point. So if it's like ice melting of Greenland, then it's all about flooding the ice. So Greenland's melting is 9 meters extra. So that is, you cannot stop 9 meters. You cannot save London, for example. That would retreat and build London upstream. Big cost, no? But melting Greenland takes many centuries. But it's a tipping point in the sense that once, like, it's a glacier of 2,000 meters high, but part of the reason why it's so cold is that it's high. Once it starts melting, and now it's only 1,000 meters, the fact that it comes lower makes it also warmer. And so although you then say, okay, oh bad, Greenland is melting, we're going to cool the Earth, it's too late, it's too low, and it will melt whatever you do. Yeah.
I think Simon talked about this in GY427, like he assigned probabilities to each like terrorist events, and then that kind of calculate the SEC. But he said theoretically, actually, it can go negative. Then go infinite. This discount rate is like negative. So SEC can actually go infinite. So how so I saw the change here is kind of modest.
Yeah.
How do you price that infinite growth? Like you can't even put a price on it
because of what I said or because of what Simon said?
Like from this table. I can saw the percentage change.
Yeah. So why? Let's give you the numbers. So given some damage function, basic damage function, some discount rate, he starts at a carbon price, optimal carbon price of 5 years ago, 52. Then you add the tipping points, you're at 67. Your carbon price goes up at with 30%, so to say. That's the outcome of their paper. Now, what are the big ones? Greenland, no, permafrost carbon. So we don't know very well how much methane is in there and how much defrosting there will be and how the regional pattern of warming is. But it's very bad. It's 8% increase. And one of the reasons why it's not crazy is that there is discounting going on. And so none of the tipping points come super early, except sometimes they include the melting of the North Pole. But it's hardly a tipping point, like it's definitely going to happen. And the effect is modest. Let me think, SAF. No, it's in here. Arctic ice, sea ice surface albedo feedback. So albedo feedback is that ice reflects light. Now, if it's molten, then you get water. Water is dark and absorbs heat. So once the ice is gone, you warm faster. And that is like a mechanical thing. So this is not that this is a good thing. The carbon price goes down because the standard model has already an albedo effect. They take that out because now they're going to for a very particular albedo effect, and the timing of this albedo effect is such that it's lower. So don't interpret this as if it's a desirable tipping point. It's not desirable, it's bad. But it has a small effect. The other big one is ocean methane hydrates. There's not much to do about this. We understand it very badly, but there is an enormous amount of, like we could call it, frozen methane in the surface, deep surface of the oceans. And if we would mess with that, then it's very bad. You get several degrees extra. And it's obviously irreversible because you're not going to bring it back. But it comes late, and therefore you get 13% increase of the social cost of carbon. So the conclusion here is tipping points are very bad. And then you can make a model and try to put numbers on that. Yeah.
What is done with the tipping points that we have already reached?
They're in the first estimate, but which one do you have in mind particularly?
No, the thing's just, for example, with the methane one, I thought there was like a study published recently that it was like, yeah, most likely already reached or something like that, but maybe I misremember this. I'm really trying to stay aware of this scientific side of this sometimes.
Yeah. So we're definitely gonna get methane feedback from the permafrost. It's happening now. We've defrosted 500 kilometers. So the methane is coming out, and we see a high increase in methane concentrations. So in that sense, would we call it a tipping point? There is this discussion, like there are 10 definitions of tipping points, but if you define it broadly as bad things that can happen, it's a very uncertain, very bad thing. But it's definitely happening in modest amounts, and then maybe it's very bad, in large amounts.
So it's maybe the same question, but so these numbers here, they are comparing damages, really assuming that it's going through the temperature. Because that's what's going through the cost of carbon.
Yeah, but the model has CO2, has methane, has other forcing agents, then has flooding, has forest burning, many things. So it's a model with a more specialized damage function that does other things than just, so it's not just a damage function, because the point is exactly like each tipping point has very different effects. If you think about Greenland, it's definitely about sea flooding and evacuating all the big cities on coasts. And so that the model has these specific damage functions. Good. Next idea. A lot of our emissions, so in the preceding model, so the one that I published myself, there's something very bad about this model. So that's how I started the paper on stranded assets. We're today at 55, 60 gigaton, and so the model tells you next year you go to 15. Or you do the unambitious version, you go to 30. You halve your emissions in year one. And that's not going to be possible because most emissions are related to capital. You need to get rid of your dirty capital. And so I thought, yeah, like this is bad, obviously. It was a simple model, so it's not meant to have this first 10 years correctly. And then we have a paper on stranded assets. And so here's the problem. So this is, for example, coal-fired power plants. We have 10 gigaton of CO2 per year. So a quarter of all the CO2 per year is just coal-fired power plants for electricity, mainly in Asia. So if you just keep these until end of life, you're going to do this. And you're going to go down very slowly. These plants, most of them are young. They're built in the last 15 years, 20 years. And so you're going to get 30 more years with high emissions. And so this is international energy agencies then having like a saying that we should reconvert part of this or do something about it. It's not optimal to keep all that. And then we started looking at what is the cost of giving up the dirtiest companies. And so we just took all the companies in the world for which we find emissions. Then we looked at the value of the company divided by the remaining emissions. This is the lifetime of the company. We set it at 40 years, and then we have the age of the company, of the assets. And so, the value divided by the remaining emissions. So if I close down the company, I lose the value of the company, and then I avoid these emissions. So it's a social cost of cumulative emissions. Yeah, stranding cost. Yeah.
And why is that winterized? Wouldn't that be quite important for example, when we said before we take our maximum abatement costs?
So we're interested in stranding. So we're interested in this part. There's going to be a few companies that are even cheaper to strand. Fine. Now there are obvious companies that we don't want to strand. That's also like, we're not interested in these. So the point is, this is $50 per ton. We can strand a lot below 20. It's super cheap. You can, and so I'm quite conservative. Like this is like the company, just you close down the company. In reality, part of the company can be saved. Or maybe not, but yeah. So it's very cheap to close down companies. This is just the inverse. So this is the intensity, emission per $1,000 of assets, corrected for age. And so some of these companies have 6 ton per $1,000 assets. Yeah.
I really like the idea. The only thing I'm sort of wondering about is if you have a company and it does something and provides a value, like it's a really dirty company, and then you close it down, won't there be like still demand of the market of like, yeah, we need this dirty product?
So yes. So the answer is the true cost of stranding is this cost of stranding plus the marginal abatement cost, what replaces this production. So for simplicity, we're not going to assume that people are going to consume less electricity. It's the opposite. They're going to consume more electricity. So think of coal-fired electricity plants. So you have 20 euro or 10 euro per ton because this new coal-fired plant is now closed down, plus 30 euro per ton to put solar. Solar, actually, it's zero, like it's the same cost as coal. But let's call it like 30 to be conservative. So then you have an opportunity of 50 euro per ton. That's below the social cost of carbon. In other words, these companies are repugnant companies in the sense that you close them down, welfare increases. So staying alive deteriorates welfare. Good. So then we weren't sure, maybe we don't believe it ourselves. So we had another database, it's all electricity power plants. And here it's also so it's a whole set. We have all power plants of the world, including government owned and those that are not on the market. And so this is the social cost of stranding, 5 euro. And we can strand 100 gigaton cumulative emissions, and then that continues. So if we look more in detail, the tail, like we were at 6, the intensity now is 10 if we go more into detail. So yellow is China, orange is India, red is the rest of Asia, and then Europe is purple. And Americas, that is both, North and South America is black. So very cheap. So that's why this idea of political constraint comes in. So we should have a carbon price that is maybe 150 for euro, 40 for the rest of the world, but you have to make sure it goes above 20. So that all this is replaced as fast as possible by solar. Yeah.
Does this sort of go against equi-marginal principle, and like you would sort of almost have arbitrage opportunities, because you would be inefficient if somewhere in like Europe it's an abatement is done for 99 and it's not done.
Very important. So whenever you have different carbon prices, there are arbitrage opportunities. So a government can say to an African country, I pay you $100, you abate 5 tons, so then I abate less. I don't spend this $100 in Europe, and everybody's there. But the point is, so the optimal solution is obvious, 100 euro per ton everywhere. But then, like, how do we get political motivation to send billions to China to close the coal-fired power plants there? We need trust that the Chinese government is using the money. We need acceptance in China that the Europeans are closing all the power plants. So you can easily see that the difficulties. It's not going to work. So better say like different, in the IPCC language, is differentiated responsibilities and differentiated capabilities, saying everybody does something, but the richer countries do not. And so that would give you a different carbon price. But whoever is from Asia and is going to go into government, tell them, stop investing in coal. It's going to be a stranded asset. This is not possible. And whenever we go slightly slowly towards optimal policy, this needs to be closed down. Including the Indonesian government, like if you think a bit smartly about what is the cheapest way to reduce a bit of our emissions, it's closing down of our power plant and replacing it by solar. It's quasi unbeatable. So good. So that we put that in the model, and then we make a paper. 3 types of capital, like typical macro models. Large adjustment cost. We do times 10 of standard models for business cycles to make sure that we're not exaggerating. We have some technical change in, we have uncertainty, we have, and the conclusion is stranding is fast and very cheap. And so the model, whatever we do, goes to 50% reduction within the decade. Now, it's without political constraint, no? Like, it's just, if you say, I want to, like, for lowest cost, and whoever inequity problems, we're just sending money transfers to get it also a win-win for everybody, you go down very fast. So within the decade, you're at half emissions. And so this has the whole inertia of the fact that all emissions, we assume that all emissions are related to capital, and so that you have this problem. The key thing is, with stranding just a bit of your dirty capital, you're avoiding a lot of emissions. And so then also, often in policy circles, you have a question.
Yeah, one short question regarding the shutting down of the companies. Does it also account for costs we have if we need to give out unemployment benefits to the workers there? Because it could very easily become very expensive then, because these people are also not paying taxes anymore.
It's a good question. So, in practice, this is a goal not to close down massive sectors, no? You have an electricity company, you're introducing a carbon price, you're getting exactly what we've seen in Europe. These electricity companies stop investing in coal, it's no longer profitable. They keep their installation, they keep coal as a backup for peak demand. They start investing in solar, that's much cheaper. And to the extent that they're building solar, the coal-fired power plants are less and less in use. But you get the same electricity, or you get more electricity because it's cheaper, and so you get also the same employment. These people just, or you get, so we have this 50 times larger adjustment cost than in standard macro models to account for the fact that it's actually hard. Some of these people need to be retrained because running coal is different than running solar. But the big picture is, if you take a decade to do that, then these adjustment costs are modest. Still like 20% of investment costs or so. There is a lot to do about labor. So my point of view is most of that statements on how the transition is good or bad for labor or for unemployment, it's most often bullshit. Because these studies just calculate like how many jobs we're going to have in solar power, and then they say, oh, we're going to create 200,000 jobs. I think to have an understanding of unemployment, you need a model of unemployment. In simple models, there is just no unemployment. So you need a proper understanding of unemployment. That's very hard to understand. And then you need to see how this interaction is. Probably slightly more unemployment because you would increase the problem of skill mismatch. Most unemployed people have low skills, and the transitions need higher skills on average, or at least new skills, and it would exaggerate that problem. But then for the rest, it's neutral. And after 1 or 2 decades, I cannot see why there would be differences. No, let's take back the last statement. Maybe there are long-term differences, but you need a good model to understand that. Good. So, green paradox. We haven't seen that much about the green paradox. Let's go over it. So the basic idea is, if you start with climate policy, you create an incentive for earlier extraction. People know that, owners know that the end of oil is in sight and they want to sell more today. And so then as a result, you would say climate policy is just counteracted by the feedback from the supply side. Now, and that would apply to many things. So cheaper green technology, lower backstop price, we get more cheaper oil today. Energy efficiency, cheaper oil today. rapidly increasing tax, faster than the oil rent, so faster than the discount rate, faster than the hoteling rule. So that's actually a non-optimally fast carbon price. All that, yeah, would create this green paradox, a feedback, there are two problems, or the first thing is, this is true. We've seen the logic. If you think about oil owners as profit maximizers, that's exactly what you expect. But then there are two mechanisms that are larger. So if you anticipate strict climate policy, you have a problem of investing in new oil exploration and in new oil exploitation. And so that is going to be larger. And so you get less oil, and therefore the price might not go down. Anticipation of strict climate policy also gives you cheaper green technology. And that will then decrease the backstop price. And with a extraction cost that increasing extraction costs, this will lead to less extraction.
In these models, is the price of, let's say, oil determined by the quantity as well?
Yes.
Or the pecuniary externality of just flooding the market with oil now?
Yeah. So it has this demand function like we saw in week 2. And so in the standard model, you get the green paradox. But when you add increasing extraction costs, that is, I actually updated, so there is a solution you can solve yourself, or there's with increasing extraction cost, and then it shows that with increasing decreasing backstop price, you exploit less in the long run. There is more and more oil that becomes uneconomic. Yeah. Now you have to take into account that if you have this feedback of the oil sector, that in your climate policy you have the carbon price and the extraction costs. That should be higher than the marginal productivity of fossil fuel, your marginal abatement cost at 0. And so if you expect a feedback from lower oil, you just increase the carbon tax and your dollar. And then you still have any temperature path that you desire. It's a nice insight because that means that the big losers are the oil producing companies, and big blocks like China, India, and Europe could win because now they get for the remaining oil a lower price. They just have to tax it enough. So one student that did a dissertation on that, to what extent that would be an equilibrium. Like you would have enough winners, and then you would have Saudi Arabia, Venezuela, the losers. Good. Just, there is much more oil than we can burn to stay below 2 degrees. So sadly, we have a problem of abundance rather than scarcity. And abundance is much harder for markets than scarcity. I have no more time. Oh no, I do have 2 minutes. So, technical change. I just published a paper on technical change last year. It's an overview, and we do, and so the big image is the following. Exogenous technical change is technical change that happens anyway, whether you do climate policy or not. Think about, you have batteries in phones, they're going to improve just by making phones, but it's also going to be useful for batteries for transition. It's lithium-ion technology, and it's going to be helpful. Just by waiting, you get cheaper batteries. So then, the fact that you have this anticipation of a cheap abatement world, you do less today. So technical change, exogenous technical change, reduces the effort today because you know that it's going to be easy in the future. Then, when it's endogenous, you have the same logic, but there is another thing going on. You again flatten the carbon price, Because if I abate more today, I get my cheap solar panels earlier. That creates an incentive for early action. This incentive is absent in most of the IPCC models. There are 2 models that do it properly. So here is the co-state equation when you have your with technical change. To make it simple, we say technical change depends on cumulative abatement.